Hey y'all, it's Sean Maxwell from ProClimate and ATTMA, the Air Tightness Testing and Measurement Association. So I'm going to take you through a blower door test of a tight building that's striving for passive house. They're still in progress. And then I'm going to give you some tips on things you can look for and ways you can think about air tightness for really tight buildings. Also going to have to give a plug for ATTMA because they are going to be your friends in the fight for better buildings. So just do yourself a favor and Google ATTMA Australia, and what will pop up right away is a list of registered air tightness testers in Australia. Some of these testers are level 1, some are level 2. Level 1 is for testing small buildings, level 2 is for testing larger buildings, multiple fans, and there's an additional accreditation for passive house testers. This is good.
What are you doing, Sean?
So I'm going to do just real quick, really rough blower door test that any builder can do to check their progress along the way. The blower door results are expressed at 50 pascals. So you turn the fan until it reads 50 pascals, and you read the number, and then you divide that number by the volume of the house. You get the number of air changes per hour. Okay, so say you do a blower door test on your house, and you turn the fan up to 50 pascals. You write down the leakage number. It's 150 cubic meters per hour of air leakage going through the fan at 50 pascals. So how do you compare that? Is that good or bad? Well, if you take that blower door leakage number, 150 cubic meters per hour, and you divide that by volume of cubic meters, say there's 300 cubic meters in this house, 150 cubic meters per hour per 300 cubic meters of volume is an air change rate of 0.5 ACH 50. You can also divide that by surface area for another way of comparing things. So often houses have a similar surface area and volume. So you would say this house has equal volume and surface area. If you divide the leakage number, 150 cubic meters per hour, by the surface area, you get a permeability of 0.5. It's pretty common to have very similar permeability and air change rate. So this is important because this is what codes are mostly going to be using, is a surface area metric, because it accounts for leakage performance in any shape of house. The leakage is 500 cubic meters an hour. 500 cubic meters an hour divided by 500 cubic meters of volume equals 1 air change per hour. It's simple math. So turn this blower door up until it reads 50 pascals. Roughly, let's see what happens. Turn it up. I'm depressurizing, so the fabric is coming towards me. You'll see what 50 pascals feels like real soon. So on the left we have building pressure, 38, 40 pascals right now. And on the right we have airflow that is required to make that pressure. One really basic thing you can do is when you're using a blower door, you can try to find out where's the leak happening. Is it at the exterior weather resistive barrier, exterior WRB, or is it with the interior air barrier? You can just look at the blower door test results in both positive and negative pressure directions and learn some things. So this test was done in both directions, positive and negative pressure, and if you look at the graph, you can see under pressurization, it's leakier. So that tells me that there's a problem with the exterior WRB, that as you push out, as you put positive pressure on it, that exterior WRB lifts up and lets air squeeze out in the picture on the left. Under negative pressure, it sucks closed. All those leaks on the outside suck closed. So that's what happens when you have a problem with the exterior weather resistive barrier. When you have an interior air barrier product or system, often the depressurization mode is worse than the pressurization mode. So when you're pressurizing on the left graphic, you're pushing that interior air barrier closed, you're pushing it tight, it seals tighter. Under depressurization, you suck all those leaks open, they lift away from their staples and more air leaks out. So that's how you can use a blower door test very simply to say, to help you diagnose some problems. So just really roughly speaking,
we're around 50 pascals, between 48 and 52 pascals, somewhere around 50. So this is the leakage number right now. It's about 1,200 cubic meters an hour. What I can do is tell the fan, try to get to, I'll put it on automatic mode and tell it, try to stay at 50 pascals. So I'll tell it, go to 50 pascals, and we'll let it do its thing. And we'll go and find some leaks ourselves.
Does it say anything if it takes some time to get to 50 Pascal or if it's easy to get to 50 Pascal?
With passive houses, because they're so airtight, you have to really be gentle with the fan pressure. If you turn it up too fast, there's not a lot of air leakage coming in to replace that air that's being drawn out by the fan. So you can change the pressure in the building really quickly with just a little volume of air, a little airflow. So you have to be really touchy. It's almost like an artwork, art form, testing a passive house, because it's pretty unforgiving. Also, things like wind have a really big influence on the pressures.
So I'll say something else about ATTMA here. ATTMA has this technical standard L4 for measuring air permeability in passive house and low energy buildings. It's pretty good for describing some of the challenges for testing passive houses. It's freely available, and it also gives some useful guidance on things like calculating the volumes of the passive house according to the standards. And it's really useful to sort of get consensus on all this stuff. So this guide was developed in partnership with Passive House Trust in the UK. And we'd like to make sure that any tests that are being done on passive houses are being done by these ATTMA testers that have gone through this extra step of training, because it really will help improve the quality across the board.
When you get a test by a passive house accredited ATTMA tester, they've seen these problems and they've gone through the reasons why they happen, and they go through ways to fix them. So there's lots of ways to correct for wind problems and fan adjustment problems and pressure fluctuations. All that stuff is just normal part of testing a passive house.
So there are courses coming up, and there are courses all the time throughout the year. So this one is for air tightness testing for passive house training for Australia and New Zealand. It's going to be online, delivered from the makers in the UK. And they really want to get us to be doing things around the world in the same way, keep that quality up.
1235. So if I take this off for the moment, and just see, before I take these up, we will try to adjust for 50 pascals. We'll see how much these leaks count. This is about 1280, 1285, something like that, which is about 50 cubic meters an hour coming through these two things. So that's right there. You can see leakage and you can see how much that's worth. When you're going around a passive house, you can say, like, okay, I have to make up, I need to cut, where is 1,000 cubic meters an hour of leakage coming from? So, and then you start to get a sense for what does that mean in terms of how big of a hole am I looking for? Or how many holes am I looking for? Just because something doesn't look sealed on the inside doesn't mean it's actually going to be a leak. This might be sealed on the far side. So it might not be a problem.
It's just a big one, Sean. I just hear a noise. What do you think is the noise coming from?
You'll hear lots of interesting noises when you're doing a blower door test. It's a whistle. And I'm trying to see, where's it coming from?
So would you say it's a typical whistle sound from a conduit, or is it a bird flying around, or what do you reckon?
It's definitely, because it's constant and it's the same pitch, the pitch will change if the pressure changes. So at a higher pressure, the pitch will go up. At a lower pressure, the pitch will go down. It's a musical instrument. Mm-hmm. So I'd say that's a tune of 50 pascals. So, but when you hear those whistling noises, those tunes that come whistling, fluttering, I'd say a whistle is better than a flutter.
Then you have a proper hole, it might be easier to find.
Yeah, so it's just the way that the air flows through a particular leak. It's not that every leak has to whistle or whine, but you'll get whines and whistles and gurgles and bubbles. Those are just noises of the air makes going through holes.
So this might seem like an obvious question, but when you find a leak and you tape it up, does that make every other leak leak more? So you find one leak and you tape it up, does that make the next leak that you tape leak more? Like you could say if this were, well, think of it this way. So this might seem like an obvious answer, but let's go through it anyway. If you find, so this might seem like an obvious answer, but maybe it's not. If you find one leak and you tape it up, does that make all the other leaks in the house leak more? So it doesn't, and here's why. So the thing that's driving the leak behind the airflow through the leak is pressure. It's like pressure in a glass of water with a leak at the bottom. As long as the height of the water stays the same, the pressure behind that leak stays the same, then it doesn't matter how many holes you poke into the can, it's still they're all gonna leak the same. So if you tape up one leak, the next one, if you keep the leakage at 50 pascals, the same pressure is going to be the same. Same amount of leakage, same amount of leakage, same amount of leakage, same for each one. Because the pressure behind them is 50 pascals, and that makes all leaks of the same size leak the same.
Okay, so we got the fan back up to 50 pascals. Who knows what happened? Someone stepped on a hose or something, so the fan shut down, but we got it back to 50 pascals, and now we're going around finding some more leaks. We wanted to know, does this little gap in the tape actually leak? You can feel, it's a little hard to see with the smoke pencil, but yes, indeed, it is flowing through here. There's a tiny bit of leakage coming through here. So what causes leaks like this? Or why is this not sticking to the membrane that's being used for the air barrier? It's because in this case this is a pressure sensitive adhesive. So this product needs a pressure tool to press the adhesive into the surface of the membrane to create a good lasting connection. Lots of different products have different needs. They're roller applied products. Others use blades to press them in. But whatever it is, you need to make sure you're following the manufacturer's directions for creating a good seal, good durable seal.
You see it's right away.
It's interesting. One interesting thing, let's look at this. One interesting thing is, when we were standing there, I just heard the whistling change pitch. It was whistling and then it wasn't whistling. What's changing between whistling and not whistling? Well, it's Jeremy standing against this window. When he's pushing against the window, the wind increases and the whistling increases, or the pressure increases. So that means that this, let's go for a second. Huge leak, huge leak. This, the fixings on this are not yet finished. Here, let's use our leakage detector here.
Nice. Where can I get this leakage detector from?
This leakage detector can be found on any job site with rubbish.
Ah, so we don't have to buy it?
You do have to buy the raw materials, but then you get this, it comes free with purchase of raw materials, these leakage detectors.
So it's actually, if you buy Proclimer tapes, it's a free product.
That's right. The backing, Proclimer comes with free leakage detector backing tape.
Cool bananas!
Actually, any manufacturer of tape comes with free.
Oh, come on, fuck on.
The sound that changes when you have leakage here, you can of course hear the wind whistling through here like a storm. But then once you put the pressure on this to close that leak, you can hear the rest of the building start to whistle.
I'm just gonna go back and then we have some
Sure.
voiceover. Okay, no.
Just pushing this door closed causes the pressure in the building to really rise fast and the fan to make an adjustment. And you can hear the building going whistling. It's through all the leaks. If you relieve that pressure by taking this off, the flow goes up by hundreds of cubic meters an hour, which could be the entire leakage budget for a passive house, just from one door. Passive house components are things like windows and doors and other things, which they go through quality. There's marks standards for quality, and one of those standards for windows and doors is air leakage. So to be a passive house component, you need to be less than a certain amount of air leakage. So if you have a problem if you're doing a blower door test, you can find out, is it a problem with the component or is it a problem with the air barrier material? So let's look at material.
Does it help when you do blower door test? Is it just helping to verify the quality of the install of membranes, or actually are you able to verify the quality of the install of most of the products of the building, like building envelope, windows, ductings, pipings?
So the blower door tests the house as a system.
So we need to get this basic terminology down as an industry here. When I say materials and components, so materials are the things we often think about with passive house and air tightness, like as an air barrier material. There's lots of different manufacturers to like to claim that they're the best, but really an air barrier material is like a sheet product or something. But that's joined together with accessories. Those are tapes and things like that at all the joints, and then they're punctured by components, and the components are the windows that I was just talking about. Those the materials, accessories, and components go into assemblies like a roof air assembly and a wall air barrier assembly and a floor air barrier assembly. Those are all part of the air barrier system. That is the thing you're testing with the blower door, the whole system, all those pieces together. So an air barrier material might be a wrap. The accessories might be the tapes to connect the wrap. And then the assembly, a wall assembly, for example, is the wraps joined together by tapes. And those are then punctured. Your lovely air barrier wall assembly is punctured by components. And if those are not good components, that can be your failure point. So when you're doing a blower door test on any house, especially a passive house, you can find out where's the problem. Is it a problem with the material, an accessory, or a whole assembly, or is it just one component? In this case, this image is from Blower Door Services and Team Catalyst. Peter Shea was doing a blower door test on a house, and with a fog machine could see fog leaking out of the window itself. That is a passive, that it could be in your passive house project, a passive house component. That's just one specific part of the building envelope. But there might be a problem where, say there's air leaking around, not out of the window itself, say this is a different wall, but there's air leaking out around the crack around where the window goes inside. It's not leaking out of the window unit itself, but the joint around it. That's a failure of the wall behind that component, that facade. So the facade brick is really just a good raincoat to protect everything behind it. And the failure point there is no taping of the sarking to make a proper membrane, to make a good air barrier assembly. A wall air barrier assembly is missing or defective in this case.
So the material, accessory, assembly. That's the terminology that you need to use, and components.
Is it? Do you think it's more important than before that all trades work together, or should, like it was in the past, that should everyone work against each other more or less?
Whose job is it to deliver the air tightness result? It's the builder's job, and the builder is the boss of all the trades, all his subbies involved. So the carpenters, the painters, the electricians, the plumbers, the insulation installers, the carpenters, they all have a part in the success or failure of this building as an airtight building. So think of the builder as the conductor of the orchestra, where he has to say, okay, now it's time for the plumber. Please, plumber, do your thing, do what you need to do, and finish up properly. Good. So, and then he has to then go through coordinating all the other trades together. He's the one that's leading the symphony, and the symphony is a passive house symphony. If there's anyone who's out of tune, the whole thing gets messed up. Or if anyone misses their timing, you could say, gets the timing off, it's going to mess up the symphony.
Whose job is it to deliver airtightness? Is it the facade company's job? Is it the painters, the finishers, installers' job? Is it the carpenter, the insulation company these days? Is there an airtightness company, Airboss Dan or someone like that? He is very good, but is it always his job only? Whose leak is it anyway? Well, if you think of the building as a system, like all the things that can leak, it's not just the wall assemblies, the ceiling floor assemblies. It's also the windows and doors, the components that penetrate through them. It's all the things that puncture your building assemblies, electrical penetrations, plumbing penetrations, HVAC penetrations. All these things factor into the performance of this as a whole functioning air barrier system. That's what you're testing with the blower doors, the system. So, whose job is it to deliver airtightness? It's actually the builder's job. The builder is like a symphony conductor. They're telling the carpenter and the facade installer when to start, when to finish, when to come on strong, when to do a little more, when to add a little more finesse, a little more tape maybe. But they're the ones that all have to work together to deliver the final product, which is an airtight building. And it's the builder that needs to be in contact and keep a handle on how this is all being coordinated, big picture.
We're at about 50 pascals across the building, across the whole envelope. So there's different layers to airtightness. There's an interior air barrier in this case. There's an exterior weather resistive barrier, WRB. Which one is doing more of the work? Is it the interior air barrier or is it the exterior WRB? Where's the failure? You can use a manometer to help you find that out. So even if you only have one manometer, you take that manometer, bring it to 50 pascals, and then take the manometer from the blower door and then bring it in your hand with one of these steel pokers and poke it right through the membrane and read what is the pressure across there. So we've got 33 pascals. Here's how this is supposed to make sense. I'll give some graphics to show you more, but if you have multiple layers of airtightness, multiple membranes, exterior weather resistant barrier, interior air barrier, and you want to know where is the problem. This is a really gross simplification of this, but here's what it means. If we're reading 50 pascals across the entire envelope, but only 33 pascals across the interior air barrier, that means that some of that 50 pascals is being taken by the exterior weather resistant barrier. So if the exterior WRB and the interior air barrier were doing equal amounts to for the air seal, then the pressure across this would be 25, and the remaining pressure would be another 25, equaling 50 pascals. If we're reading here at 33 pascals, that means that the exterior WRB is only providing 17 out of those 50 pascals of pressure resistance. It's almost like you can draw diagrams like this, almost like electrical resistance. If the whole voltage across the whole thing is 50 pascals, well, there's a resistor with the exterior WRB of 17 ohms, or 17 pascals, and then a resistance here of another 33 pascals. And then you say, which resistor, which is the weaker resistor? The exterior WRB in this building, at least on this wall, is doing less than the interior air barrier. So that could mean a couple things. It might mean that you walk outside and you look for problems with the exterior WRB. Is there a big failure somewhere that's feeding a bunch of air into this wall assembly, which the interior air barrier then has to deal with?
So think of these as leaks in series. This is gets a little bit esoteric here, but really that's what these are. You've got leaks in series, or air barriers in series. You've got the exterior weather resistive barrier and you've got the interior air barrier. So where's the failure happening, or which one of these is taking more of the load? Really, just think of it this way. The pressure across the entire building is 50 pascals. If that were that pressure resistance were provided equally by the interior air barrier and the exterior WRB, if you poke a hole into the space between them, the pressure across that hole should be 25 pascals. In other words, 25 pascals of resistance is coming at the exterior WRB and 25 pascals is coming across the interior air barrier. If it's more or less, that tells you really which one of these resistors is taking a greater share of the resistance to air movement. Is it the exterior WRB or is it the interior air barrier? And you can use a chart like this to really understand it. And the more you do this sort of thing, the more you sort of reason it out yourself.
You can do a conversion. The blower door software, in fact, the manometers in real time can do a conversion between air leakage and estimated leakage area. How much leakage area, roughly speaking, does this represent? And for this particular house, it's probably a combined whole of something like this size for the entire house. You're allowed this much leakage for the entire house. Does that blow your mind? That's all you're allowed for this entire place. And so as you're walking around looking for leaks, you have to think, okay, there's a little sliver right there. What's the leakage through that? There's a little electrical penetration there. What's that worth? You just start adding it up and remind yourself that all of those little leaks you find have to fit in this little box. So I was going to say, with when you're looking at leaks, if you find leaks and you want to know how important they are, one general concept is that bigger leaks leak more than an equivalent collection of smaller leaks. This is fluid dynamics. So if you take this thing and you cut it up into smaller holes, say this is 50 square centimeters, and then you cut this up into smaller holes, which one of these is going to leak more, even though they represent the same area of leakage? Well, because of fluid dynamics, there's a lot of air turbulence going through these smaller holes, and so the turbulence creates friction, and that reduces airflow. So these, even though the collection of these is the same size as this single leak, the single leak will leak more than the collection of smaller leaks because there's more resistance through a collection of many smaller leaks than there is through one big leak. So people often ask, is doing the blower door going to contribute to leakage that wouldn't normally be there? Can you seal around this during the blower door test? Yes, you can. You can seal around this here with some extra tape, gaffer tape or something, to make this seal better during a blower door test. They also ask, is leakage like this, where you pass a hose or a power cord through, going to contribute to the leakage? Yes, but it's a very small leak, and again, try to keep the big picture in mind. Is that what's making you fail, or are there many other leaks that are making you fail? There are ways to use these little grommets here, little nipples, to get rid of that leakage entirely. So if that's your failure point, then you're doing a good job.
Okay, so I'll say this one last time. When you get a test done, it's really great to have it done by an ATTMA tester, Air Tightness Testing and Measurement Association's worldwide group of really committed people who really want to see this industry thrive, and they are your partners, absolutely, in the pursuit of air tightness. If you get an ATTMA tester, make sure that they take the Passive House training add-on, which helps them do better calculations, helps them deal with the complexities and difficulties of testing the ultra-tight houses like Passive House. Also, it's a really good idea for your builders to get their own blower door, or for you as a consultant to get your own blower door. Then you can find problems. Even if you don't do the ATTMA course, it's really just a great tool in your tool belt, in the back of your truck, to get better results, to see real-time improvements in air tightness and get better and better and better at it. And when you're done, you can pass it on to someone else who's in need of a good job testing houses. So hope this was helpful, and I hope I can answer any of your questions. Thanks.